Can you hear me?
Yes, morning, sir.
Okay, so today we are going to continue for the chapter integration. Just only to remind you, it's last class we were talking about the integration using Trapp's rule and Simpson rule. So we are saying that it's to calculate using the Trapp's rule. Maybe you can go for single application of Trapp's, or to increase the accuracy of the integral. Maybe you are going to use multiple segments of trapezoidal. And if we are going to talk about I call it's the Simpson rules, we are having two types of rule of Simpson. It's 1 over 3 and 3 over 8. And here is the difference between these two rules. It's the number of the points and the number of the segments. So for 1 over 3, it needs about 3 points. These 3 points will create for you 2 segments. 3 over 8, it's creating 3 segments coming from 4 points. We are going to use these rules, and we are going to use those points to help us to solve that type of questions which is coming from integration with unequal segments. As I told you last time in the class, the question is not going to be asking you directly to use Trapp's rule or to use 1 over 3 or 3 over 8. The question will come and asking you to use the inclusion of all the methods together, all the rules together you need to use to calculate for the integration. So to start for our class today, we are saying like in practice, there will be many situations when you are going to deal with the data or the points of x. Those values, they are not going to be in equal space, different size. You're not going to have the same step size. So how you are going to deal with it? So in that case, there will be one method could be applied, which is trapezoidal rule, 2 segments, and sum the results. So that's mean, let's say for example, you are having this curve and you are having multiple segments here, but actually those segments, they are not equal. You can see the step size from here to here is not the same step size from this, and also the step size here is really small. So you can see from here it's different step size. So what you can do here is you are going to deal with all segments in here as a traps. So this is traps number 1, this is traps number 2, this is traps number 3, this is traps number 4, and so on. So what you're going to do, you are going to calculate the equation for the first trap, and the equation for the second trap, and for the third traps. And at the end, you are going to total them up. Okay. The other methods in here, which is mostly you are going to do that if question is asked, you are going to do the inclusion of the Trapp's rule and Simpson rules. Only the question is coming from this point. So how to do this? I'm going to show it to you. We are doing the example. So we are having the example with the given data from this function. So this is the function, and this is the same function that we have built before. But now we can see that it's the values of x is given, they are not in form of same step size from 0 to 0.12. So the step size here is 0.12. From 0.12 to 0.22, the step size is 0.1. You can see here from 0.36 to 4, it's 0.0. So that's why it's unequal segments. So this example asking you to use the following method to determine the integral of this data. The first, we are going to go for the Trapp's rule, and next we are going to make the inclusion of Trapp's rule and the Simpson rules. Okay, so first let's see it how we are going to do that using the Trapp's rule, which is the easiest one. I'll open my Excel file. Okay, so this is the data came from the example. This is the x and this is function. So we are going to divide the whole area from x to 0 to 0.8 we are going to divide it into all traps. So this is the first segment of the first trap. This is the second segment for the second traps. And this is the third segment for the third traps. And at the end, we are going to total up all the integral. So first, I'm going to calculate the first segment. My first segment is b minus a. So it means 0.12 minus 0 times the function of a, 0.2, plus the function of b, 1.3 over 2. So when I'm making my calculation, I will get the answer is equal to 0.09. Then I will go for the second segment, from 0.12 to 0.22. So b minus a, this means 0.22 minus 0.12 times the function of a, 1.309 plus 1.305 over 2. We get the answer here is equal to 0.130. So you are going to continue all the calculation in this form till you get the total up of this column. So when you get the total up of this column, this means you already get the integral of that one. So I don't want you to do the example from Z. I just want you to try it with. I want you to try to find these two values. So I will give you about like 2-3 minutes to find those values. Then you are going to compare your answer with me. If you have any questions, please do ask how to do the traps, which is actually we already have done it in the previous class, but I want you to do it for these two, just only to check that you can understand how to get that answer. If you have any questions, please do ask. You get the same answers for these two?
Yes, sir.
Okay, so this means you are going to continue with the rest of all the segments. But I don't want you to do it. It's tedious work. So at the end, you are going to total up all these values. So you get the answer is equal to 1.59. Okay. In the example here, is giving us the true value. This is the true value given in the example. So when we back here, we have the true value minus our result is coming from the total up. So this is the error is going to be equal to 0.05. We want to get this answer in percentage. We divide over the true value again. So we get the answer of 2.7. Okay. So, but this one is not our concern. Our concern now is how to do this one with the inclusion of Trave's rule and Simpson 1/3 and 3/8. How we are going to solve it. So to do this, I'm going to just explain it here first before we start. Okay. Let's say that it's my function is something like this. This is our segments. Okay, so to use the inclusion of all the methods to be solved and to get more accurate results, so we need to look at the step size. The most important thing is here to check the step size. If the step size is equal to each other for some points, so this means we can use 1/3 or 3/8, and also based on the segments. So how to do this one? First, we start to calculate the step size for each segment. So I have here from 0 to 0.12. My step size is 0.12. So now I'll check from 0.12 to 0.22. The step size is 0.1. So this means these two step size for these two segments, they are different from each other. So this means I cannot combine this segment and these segments. I cannot combine them. So this means I can solve the first segment here using Trapp's rule. So I will solve the first segment here for Trapp's rule. Okay. So now I will check again the step size for the coming segments. It's from 0.22 to 0.32. So the step size is 0.1. Now it's from 0.32 to 0.36. Step size is 0.04. So this means I have two segments with the same step size. Two segments with the same step size and 3 points. Which rule I can apply? 3 points and 2 segments. What type of rule that I can apply for these 2 segments? One over 3. So I will apply here 1/3. Good. So now we'll check again from 0.36 to 0.4. Okay, the step size is 0.04. From 0.4 to 0.44, the step size is 0.04. From 0.44 to 0.54, the step size now is changed to be 0.1. So that means I cannot combine these segments with these 3 segments. So now what I have here, I have 3 segments. 3 segments with 4 points. What type of rule that I can apply it here?
3.8 rule.
3 segments and 4 points. So I will go for 3 over 8 for all these for all these 3 segments. Okay, so now from 0.54 step size is equal to 0.1, and from 0.64 to 0.7 it's 0.06. So that means I cannot combine these segments with these two. So I have here 2 segments with the 3 points, so I will apply 1 over 3 here for these 2 segments. Okay, now from 0.7 to 0.8, the step size is equal to 0.1. So 0.06 and 0.1, this one cannot combine because different step size. So I will apply traps rule here and I also apply traps rule here. So I end up, after you calculate all this 1 over 3 and 3 over 8 and 1 over 3 and traps, you are going to calculate, or you are going to sum up all these values. How to solve this one? I have done it here. I will give you a time. Let's say I'm going to give you about 10 minutes. Take about 10 minutes to solve this example complete. Find the equation of Simpson 1 over 3 and 3 over 8 and try to get those values of the integral. Okay, so this is your table. So you need to find these values. And at the end, you are going to total up. And the answer here, 1.60. This is the true value minus our result. So you get the answer of 0.36. So the error here is going to be less than what we have here. If we are using all traps, it's the error, it's 2.78. Now it's 2.24. Okay, try the example, and if you have any questions, please do ask. I will give you about like 10 minutes to solve it all, but please solve it complete, because this is the type of the question is coming in, whether it's going to be coming in the final or for the assignment too. Okay, that's good. So getting the same exact answer. So that was all for the integration. Okay, our next topic is we are talking about the numerical differentiation. So we are going to cover the high accuracy differentiation formula. And the new things here just only today is the Richardson extrapolation method. This is the only thing is new. So at the end of this topic, you'll be able to identify and apply the methods for to differentiate formula and the data set. So before we start is what's the meaning of the differentiation or the derivative is giving. The derivative it's represent the rate of change of dependent variable with respect of an independent variables given by mathematical definition, begin by the difference approximation. So if you are looking at this mathematical definition for it, you have here dy over dx, and we are having also the function and the delta x here. So delta y, delta x, which we are having here y, and the function this is considered the dependent variable, and x here is considered the independent variables. So if the delta x is allowed to be approaching zero, so the difference become the derivative. Most of these things you already know it, and we already explained it at week 2, I think, when we were talking about the forward finite divide difference and the backward and the center finite divide. So we said that it's when the question is coming, you are going to have an initial value of x. And when the question is asking to find the forward finite divide, so that's mean you need to find xi plus 1. And if the question asks for the backward finite divide, so that's mean you need to predict the function at x minus 1. Center finite divide is taking the whole range between x plus 1 to x minus 1. Okay, so quickly this is what we have, the initial value of x. To go for the forward, so we need to predict the function at xi plus 1. So we need to know what's the function at this point. And from x to x plus 1, this is considered h, single step size. Backward is the same. This is the initial value of x. To go backward, so we need to predict what's the function at x minus 1. And from x to x minus 1, this is single step size. Center finite divide taking between plus 1 to x minus 1. That's why here it's 2h, two step size. Okay, this is what we had learned before. Today we are going to go for the high accuracy differentiation formula. So high accuracy divided difference for the forward and for the backward and for the center formula. It can be generated by including additional terms from the Taylor series expansion. So this means, remember, when we are talking about the Taylor series, at the first week, we are saying that Taylor series, if you take just only the zero order, the accuracy is not going to be high. But if you add more terms for the Taylor series, you are going to get high accuracy answer and are going to reduce the error. So what actually we are going to do here for the high accuracy differentiation formula for the forward and the backward and the center, we will add another terms. Previously, we are talking about initial value of x and xi plus 1 and xi minus 1. Adding more terms, so this means I will add xi plus 2 and xi minus 2. And this values is going to be included into an equations to get more higher accuracy. So this is what does it mean about high accuracy of difference formula. You need to add one more terms for the backward and for the center, and also for the forward, backward, and center. Okay, so to look at what we have done on the second week, the equation that we use the first equation for the first derivative. We use this equation to find for the forward finite divide. We call it OH because this is a single step size. And you can see that for the equation is equal to the function of xi plus 1 minus the function of xi, single step size h. We call this one is OH. To go for high accuracy for the forward finite divide, we say that we need to add xi plus 2. So that means we are going to use this equation. Why? Because here xi plus 2. So the equation for the forward finite divide for high accuracy of the function xi plus 2 plus 4 of the function x plus 1 minus 3 function x, and this is 2h. That's why here we call it OH square. Okay. The same button also to do the same with backward finite divide. Previously, without high accuracy, we just using x and x minus 1. But now to go for more high accuracy OH square, I need to add xi minus 2. And this is the equation we are going to use for the high accuracy formula for the backward finite divide. Same goes also with the center finite divide. Previously, OH square, because this is two-step size, we are talking between xi plus 1 to x minus 1. But now for OH power 4, more higher accuracy, we are taking the range between xi plus 2 to xi minus 2. So this is the equation will be used to calculate for high accuracy center finite divide difference. The good thing is that what we are going to do here is this example that we are going to do it here is the same example that we have done it at week 2. So the first part we already have done it at week 2, but now it's just only we are going to start with initial value of x is equal to 0.5, and we are not going to do it with h is equal to 0.5. We are not going to use this. We are just only going to use h is equal to 0.25. Why? Because remember last time we said to reduce the error, maybe you need to reduce the step size. So if you reduce the step size from 0.5 to 0.25, this is going to be increase or to reduce the error. So now here we are going to use part E, which is use high accuracy, because part A we already have done it at week 2. So we are not going to do this. We are going to use the high accuracy formula finite divide difference for the forward, for the backward, and for the center. Okay, so just only to refresh back your mind, we are going to do it for the normal first, but this is not high accuracy because we just only going to use xi plus 1 and xi minus 1, just only to compare the results. So this is our function, and this is the true value. We're supposed to be the size. So first of x is 0.5. So if I go forward, xi plus 2, 0.75. Go backward, xi minus 1 is going to be equal to 0.25. So now I need to find what's a function when x is equal to 0.25, 0.5, 0.75. So I put those values, putting all the x's here. So when x is equal to 0.25, this function will be equal to 1.103. And when x is equal to 0.5 here for this function, will be equal to 0.925. When x is equal to 0.75 for all the x's, the function will be equal to 0.63. So now I can use the equation of forward, backward, and center. But this is not for the high accuracy. Why? Because I just only have x minus 1 and x plus 1. So I will use the old equations. So remember, this is for OH, this is for OH, and this is OH square. Okay, for the forward, is going to be equal to the value of this function minus the value of this function over the step size. So this value minus this value over the step size. So the answer is negative 1.15. It's not even near to the true value. So when you calculate the error, it's 26.5. Now let's go for the backward. So it's going to be 0.925 minus 1.103 over the step size. So I get the answer negative 0.7. It's not near to the true value. So the error is 21.7. Now let's see the center finite divide. So center finite divide, it's from x plus 1 to x minus 1. So this means 0.63 minus 1.103 over step size over 0.5. And somehow when you are looking at this value near to the true value, that's why the error here is going to be equal to 2.4%. This is what we have done at week 2. So now let's try to apply the high accuracy. So this means applying by adding xi plus 2 and xi minus 2 and see how the answer is going to be. So applying the high accuracy, so 0.5, this is the initial value. So to go forward, xi plus 1 will be equal to 0.75. Go for xi plus 2, so will be equal to 1. For the backward, xi minus 1 is equal to 0.25. Go another term for xi minus 2, so it's going to be equal to 0. So when I put 0 inside my function here, the function of xi minus 2 equal to 1.2. 1.2. When x is equal to 0.25, function will be equal to 1.03. This is for 0.5. This is for 0.75, and this is for 1. So what I need to do here, remember that this one is OH square, high accuracy. And this OH power 4. So I'm going to use the equations that it include the xi plus 2 and xi minus 2. So use the values for the forward finite divide. So the answer is negative 0.8. So the error is reduced. You can see it here, clear. This is for the backward. This is the answer. And the error is also reduced from 21% to 3%. And if I'm going to use the center, so the center is going to use all the terms from 0.2 to 1.2 with the values of the step sizes or 4. When you are going to look at this answer here, it's exactly the true value. That's why when you are going to calculate the error will be equal to 0%. So when you are adding more terms for the Taylor series, so it means you are reducing the error, as you can see it from here. So this is what we talk about using high accuracy formula for the forward and center finite divide. If you have any questions, please do ask. If not, then we are going to move to the last method for today. Is it clear? Any question about the center or backward or forward?
Yeah.
Okay, last method for today. Okay, so from this example here, you can see the comparison for the error between all the methods. This one is for OH, and this is for high accuracy. So you can see that from 26 to 5%, from 21 to 3%, from 2.4 to 0%. So this is the comparison. Okay, last method for today is Richardson. This is uses estimates of integral to compute a third more accurate. I'm going to explain it again. No worries for the next slide. So remember that it's we were saying that there will be two ways most of the time to improve relative estimate. The first one is by decreasing the step size, or by use higher order formula that employs more points. Remember, just right now, we are applying high order formula that employs more points. We apply x plus 1, and we add x plus 2, and also x minus 1 and x minus 1. So when we apply more terms, we are going to reduce the error. The good things about the Richardson extrapolation that it can be used to get high accuracy results, same exactly like high order formula, but we are not going to apply more points. So it means you are not going to add xi plus 2 or xi minus 2. So remember, it's for the Taylor series or for the forward, backward, and center. To get more higher accuracy, I need to add more term, which is x plus 2 or x minus 2. These methods here, Richardson extrapolations, it can have the same accuracy of OH power 4, but you are not going to be adding x plus 2 or x minus 2. So it will give you the same exact accuracy as we are going to see it from the example. So actually, is Richardson to be for the integral, is not for the differentiation, but actually we can apply it at the same time. So the equation, the formula, it's used to be improve the integral estimates of I. So where we are going to have two integrals with the two different step size, IH1 and IH2. So the integral estimates using two step size, H1 and H2. And H2 actually it's half of. Okay, so the equation actually is, this is the one we are using it for the integral. To calculate the integral, it's 4 over 3 with the integral of the second step size minus 1 over 3 with the integral of the first step size. We can apply this one also for the derivatives. So instead of the integral, we can make it for the. So we just change to. What's good things about these methods in here? H power 4 terms like xi plus 2 or x minus 2, I can achieve the same exact answer accurate as we are going to see it from the example. Okay. Remember, it's for the equation OH square, we're just only using xi plus 1 and xi minus 1 over 2h. Okay, so yeah, this is what we are going to use. And we are going to achieve the answer OH power 4. This is the example. We need to estimate the first derivative of this function at x is equal to 0.5. So my initial value of x is 0.5. And my step size of h1 is equal to 0.5. So of course, h2 will be equal to 0.25. I need to find the improve of the estimates using where exactly is my true value is this value here. So how to solve that? So first I have my step size h. So this is going to be h1 and this is h2. So remember that we are using this equation here, xi plus 1 and xi minus 1. So xi plus 1 is equal to 1. Xi minus 1 is equal to 0. Why? Because remember, it's our initial value of xi is equal to 0.5. And my step size is 0.5. So if I go forward, it's equal to 1. If I go backward, it's equal to 0. So now I need to find the value of the function. When x is equal to 0, the function will be equal to 1.2. When x is equal to 1, it's 0.2. Then I'm going to use the equation 0.2 minus 1.2 over 2 step size. So it's negative 1. With the same pattern here, I'm going to repeat with the second step size of H2, so 0.25. So 0.75. Remember, here is my initial value of xi is equal to 0.5. So if I go forward, it's going to be 0.75. If I go backward, it's 0.25. So I will find the function for these two values. It's 1.103 and 0.63. Then I will apply this equation here. So 0.63 minus 1.103 over two-step size, 0.5. So I get the answer, it's negative 0.934. And this is the error for it. So now let's apply the Richardson extrapolations method, since I have the values. So this value here is what we get, and this terms here, this answer here. So the 3 times negative 0.934 minus 1 over 3 times negative 1. So the answer is negative 0.9125, which is this value is exactly the true value. So clearly find is the relative error is equal to 0%. So now what did we apply? We apply the equation of OH square, but we are at the end of OH power 4. Okay. And this is the full answer of the example in here. I will give you about like 5 minutes to try it, and I will back with you. Then I'm going to solve the midterm exam with you. Try it first. Okay, so let's start. I want to solve with you the midterm exam. So this is the first question. This is the first question asking for the trapezoid channel is flowing with the water at a flow rate of Q is equal to 30 meter and the critical depth Y, and this is what we want to find for such a channel must satisfy the following equation. Okay, so this is the function of Y. So Q is 30 meter. So this we need to square it, so it's going to be 900. The value of the gravity constant is already given here. And the value of AC is already given by this equation here, and the value of B given by this equation. So what you need to do is just only to embed these values for A and embed these values for B. So you need to determine the critical depth using the second method. The initial values of yi minus 1 is 1.5 and yi is equal to 2.5, and iterate till the error is less than 1%. So here they didn't give you the true value, just give the approximate error. So you need to calculate the approximate error here. So how to solve this? First, you are going to make your equation. So this is your equation here. This is the function 1 minus 900 over the gravity 9.81 times the value of AC. Don't forget it's cube in here, times 3 plus y. This is my initial value of 1.5 and 2.5. Okay, so now I need to find what's this function is going to be equal to what when y is equal to 1.5. Would you please use your calculator and calculate what's the answer is going to be here? Take your time. When y is equal to 1.5, the answer of these two. This is your answer, right? Okay, so now with these four values here, we are going to use the second method's equation to calculate the new value of yi plus 1. So I'm going to put these four values inside this equation. So I'm supposed the answer is equal to 2.1949. I can calculate now the error. So the error is 13.9. Okay. That means I will go now for the second iteration. So calculate the same values. So yi minus 1 here is going to be equal to the value of 2.5, and y is going to be equal to the new value here. So y minus 1 is equal to 2.5, and the value of y will equal to the new value was here at the first iteration. Then I will do the same. So this value, we already have it from the beginning, is equal to 0.75. So the new one is 2.19. You need to find the answer for it. So put this value inside this equation to get the answer of 0.3448. And again, you are going to put these four values inside the second methods to get the answer of the new value of y, which is 1.7463. And calculate the error. New value minus the old value over the new value is 25.16%. Then with the same button, you are going to go with the third iteration. So yi is going to be equal to 1.7463, and yi minus 1 is going to be equal to 2.149. And find the function for these values. Put these four values inside the second methods to get a new value of y and calculate the error. New value minus the old over new. So it's 12%. With the same button, you're going to continue with the fifth iteration. As you're going to see it from here. The fifth iteration is your answer. It's 1.9347. Less than 1%, it's 0.59. Okay, so this is the answer for it. Most of you can answer question number 1, but it's most of you question number 2, it was difficult for you. Okay, for number 2. Just only before we start the question or asking about anything. This one is considered as a polynomial regression or considered as a multiple regression. This one is a polynomial regression or multiple regression. Polynomial regression. Okay, good. So that's mean if this one is a polynomial regression from the appendix, that's mean you are not going to use this matrix at all. This is what you are going to use. So you already have the value of x, you have the value of y. So you need to find x squared, x cubed, x power 4. You need to find the x times y and x squared times y. Okay, so this is the key of how to solve these questions. You already have x and you already have y here. So actually is g here is supposed to be y, and the a's in here is considered the x's. So you need to find them. Okay, so how to do this? So this is the matrix, and you need to find x squared. So create a new column to find x squared and the sum of it. And you need to find the x cubed. Make a new column, find the x cubed and the total up of it. And x power 4. And find the total up. And the summation of x times y. make x times y column, you get the answer. And the summation of x squared times y. Okay, so you get it here. Once you're done, you're going to create this matrix in here. Here you are having 5 points. The summation of x is 55. The summation of x squared is 769. And the summation of y is 78.2. And here is going to be 55, 769, and the summation of xq is 11,899. You just continue with all the values here. Okay, of course, the question is asking you here to use the naive-Gauss elimination methods to find knowns, right? So like the naive-Gauss elimination, I'm not going to explain how to make it, but at the end, you are going to get this matrix. Okay, you are working online, and some of you making the matrix, or they don't know how to use naive-Gauss elimination. You can just simply check your answer. If this is my matrix, I can highlight 3 by 3, and I say it's equal to M inverse. I open a bracket. I want to inverse this matrix. Control Shift Enter. So that means x1, x2, x3 will be equal to, it's equal to MMULT. The inverse matrix times the constant. Okay, so this is the answer, all the x's. Some of you, they are making the goes, but and somehow something goes wrong in the middle. So the answer, final answer is not like this. You can use your calculator just only to check your answer, or use Excel to check your answer. So if you see your answer, doing it manually is not matching Excel. So try to fix whatever, because actually it's the final exam and the midterms exam, you cannot use Excel, but actually you are using your computer, so you can do that. Okay, so now this is the values of the x's after use. You can see from here they are matching mine. Okay, 0.27, 0.42, 6.2. It came from here. Some of you, they are not getting the same exact answer here. That's why your answer is wrong at the end. So when the equation, of course, is going to be equal to, the equation is came from here. You already have x0, you already have x1, you already have x2. Put these values here. So this is x0, 6.2. x1 is equal to 0.4. x2 is equal to a. So now you need to find when a is equal to 20. So substitute 20 here and 20 here. So the answer will be equal to 26.6. So do you have any questions how to do this one? Is it clear? And easy, right? That's the answer for the midterm exam. So if you don't have any questions, that's all for today. I will see you, inshallah, for the class next week. And I am going to combine the lab for this chapter and the coming chapter together at the lab session. If you have any questions, please do ask. If not, so thank you all. Don't forget to write your name on the chat box to take the attendance. Thank you all. You're very welcome.